Imagine standing on a windswept pier at dawn, staring at a half-finished bridge tower rising from the middle of a raging river. The water is deep, fast, and merciless, yet dozens of workers in hard hats are calmly welding steel 30 feet below the surface, as if the river simply doesn't exist. How is that possible? How do you build something massive and permanent in a place that is, by definition, completely underwater? The answer is one of the oldest, boldest, and most underrated tricks in civil engineering: the cofferdam. It's a temporary wall slammed into the riverbed that says to millions of tons of water, "Not today." Pump the water out, and suddenly you have a dry construction site surrounded on all sides by a liquid wall ready to crush everything if you get it wrong. It's part Roman genius, part industrial age brute force, and still the only practical way to plant the foundations of the world's greatest bridges, dams, and offshore towers. This is the story of how humans learned to steal dry land from the sea, one steel wall at a time. Story: humans have always wanted what sits on the other side of water. Trade routes, fertile floodplains, harbors, bridges. All of it lies just beyond the shoreline or in the middle of a river. The problem is obvious. Water destroys everything we build. Concrete won't cure underwater, steel rusts faster, and workers can't breathe. For thousands of years, the solution was simple: don't build there. Then someone got impatient. The first cofferdams were Persian, around 500 BCE. Herodotus describes King Cyrus's engineers building earthen dikes around a section of the Jins River, bailing it out with buckets so soldiers could march across on dry ground as an act of petty revenge against the river for drowning his horse. It was slow, dangerous, and required an army of laborers, but it worked. The Persians had invented the basic principle: wall off a patch of riverbed, remove the water, do your work, let the water back in when you're done. The Romans turned it into an art form. When they needed to build bridge piers in the Rhine or the Tiber, they didn't mess around with dirt mounds. They sharpened massive oak trunks into piles, floated them into position with boats, then used a 10-ton pile driver powered by block and tackle and a lot of swearing legionaries to hammer them into the riverbed in 2 interlocking rows. The gap between the rows was filled with clay. Once the rectangle was sealed, they bailed, first with buckets, later with Archimedes screws and chain pumps. Suddenly Julius Caesar had a dry hole in the middle of the Rhine and a bridge the Germans couldn't believe was real. Roman cofferdams were so good that some of their timber piles are still in the ground 2,000 years later. After Rome fell, the technology mostly went backward. Medieval Europe used wicker baskets filled with clay or simple sandbag rings when they had to repair a mill dam. It worked for small jobs, but nobody was spanning major rivers anymore. The modern cofferdam was reborn in the 19th century when steel finally became cheap and strong enough. In 1908, a German engineer named August Detmer patented the first interlocking steel sheet pile. Picture giant U-shaped steel panels, each one 20 to 40 feet long, with a clutch on each edge like giant Lego pieces. You drop the first one vertically with a vibratory hammer or a diesel pile driver that sounds like the wrath of Thor. Then you slot the next one into it, and the next, until you've built an impregnable steel box in the middle of the water. The interlock is watertight enough that only minor seepage gets through, and that is handled by pumps. Here's how a big one actually gets built today. Site survey and design: geotechnical engineers drill boreholes to map the riverbed. They need to know soil type, depth to bedrock, scour potential, and current speed. The cofferdam has to resist not just water pressure but also the piping phenomenon. When water pressure under the wall is high enough to boil sand up from below like quicksand in reverse, the sheet piles have to be driven deep enough to cut off that flow, usually 1.5 to 2 times the water depth below the riverbed. Driving the wall, a barge-mounted crane with a 100-ton vibratory hammer or a hydraulic impact hammer slams each sheet pile home. On big projects, think the new Tappan Zee Bridge or the Øresund crossing between Denmark and Sweden. They'll drive 60-foot steel sheets in water 100 feet deep. The noise is deafening, the vibration rattles your teeth, and river traffic is closed for miles. Bracing once the perimeter is closed, massive horizontal whalers, steel beams, and diagonal struts are welded inside to keep the walls from bowing inward under dozens of atmospheres of water pressure. On very large or deep cofferdams, They'll install multiple levels of bracing that look like a steel spiderweb. Dewatering this is the moment of truth. Huge diesel or electric pumps, sometimes 30,000 gallons per minute, start sucking. The water level drops foot by foot. You can literally watch the river outside trying to get in. Seepage jets squirt through tiny gaps, mud boils at the bottom, but as long as the pumps stay ahead, the hole stays dry. The first time workers step onto the actual riverbed with the river raging 10 feet away on every side is a religious experience. Build the permanent structure now, it's just a regular construction site, except the site office is a steel box at the bottom of a river. They drill shafts, pour treamy concrete seal slabs, build the pier footing, and eventually the pier itself. Everything is designed so that once the permanent concrete is stronger than the cofferdam, the river can come back. Flood and remove when the pier is high enough, they pull the pumps, let the river flood back in, cut the bracing with torches, and vibrate the sheet piles out for reuse on the next pier. The only thing left behind is the concrete that will carry cars for the next century. Not every job allows a perfectly sealed cofferdam. In very deep water or terrible soil, the sheet piles would have to be impractically long. In those cases, engineers use open or pumped cofferdams. They still drive the wall, but accept that water will keep seeping in. An army of pumps runs 24/7 for months. On the Akashi Kaikyo Bridge in Japan, world's longest suspension span, the foundation cofferdams were 70 meters deep and required constant pumping against 2 to 3 meters of tidal rise. Redundant generators, backup pumps, and tsunami alarms were all part of the safety plan. Cofferdams aren't just for bridges. When a cruise ship needs to be cut in half and lengthened, yes, that happens, they build a cofferdam around the entire ship in dry dock, pump it empty, and saw the vessel in two like a loaf of bread. When offshore wind farms need foundations, circular cofferdams the size of apartment buildings are floated out and sunk. Even nuclear plants on coastlines use them to build intake structures. Risks are real. In 1915, a cofferdam on the Keokuk Dam, Mississippi River, failed catastrophically, killing 13 workers. In 2003, a pumped cofferdam for Chicago's Deep Tunnel project flooded so fast that workers barely escaped. Modern designs have multiple failure modes covered: double-walled cofferdams, automated pump systems with SCADA monitoring, real-time tilt meters on the walls, and mandatory evacuation triggers if inflow exceeds a certain rate. Failure today is slow enough that no one dies. They just lose the equipment and a few $1,000,000. The cost is staggering, often 10 to 20% of the entire foundation budget. But there is still no real alternative when you need precision concrete in deep water. Divers with Treme pipes and underwater robots are fine for small repairs, but you can't build a 1,000-ton footing with them. So the next time you drive across the Golden Gate, the Bosporus Bridges, or the new Gordie Howe span between the US and Canada, remember, every one of those towers started with a steel ring punched into the seabed and a small army of engineers who told the ocean, politely but firmly, to wait outside until they were finished. That temporary ring of steel, gone before the bridge even opens, is the reason the permanent one will stand for centuries. Cofferdams are the invisible miracle that lets us conquer water one dry patch at a time.